better. And faster being better, it's better because it's less time, right? Like numerically, the time elapsed is smaller, okay? All right, so that's going to be one of my hypotheses. Which one should that one be? The alternative, and how do I know that one's the alternative? Because there's not an equal to in it, okay? If that's my alternative hypothesis, my null hypothesis would be greater than or equal to. All right. I randomly selected a sample of 60 weekend. So I have the n for the weekend is 64. I have the time for the weekend is 21.2. And a standard deviation of 4.1. So as we're looking at that standard deviation of 4.1, is that describing the population or is that describing the sample? It's describing the sample, yes? Why is it important that we make that distinction? It's telling me we're going to be doing a t-test instead of a z-test. Are we good? And likewise, we go in and we have for the weekends, for during the week, the sample size was 81. The mean was 23.8, and the standard deviation was 3.2. All right, so knowing this, what am I going to pick in my calculator? Say that again? The two sample t-test. You guys, the way I know it's two sample, how many means do I have in my hypothesis? 2. Okay? All right, in this case, oh, lucky me. It's already in mine. So, oh, nope, it's not. You guys, in the morning class, and I'm going to leave mine as it is. In the morning class, this was mu W is greater than mu E. You guys seeing, okay? Like I just did it in the other direction. I want to show you guys that we get the same thing. So as you guys are typing this in, because the weekend group is the one I wrote first in my hypotheses, that's what I'm going to put for X bar 1, S1, and N1, okay? In my calculator, I have them backwards because I did it in the other order for the other class, but I want to show you kind of, we end up with the same thing, okay? So I'm going to let you guys put these ones in the correct order. I'm going to leave mine in the different order so you guys can see what the different answers look like. So, my bet is that when you guys hit enter, you found t equals negative 4.168. Is that correct? Okay. You'll notice in my picture, or when I put it in going in the other order, I got t equals positive because I'm doing it backwards. I'm doing the other side. Now, but I bet our p-values were the same. For my p-value, I got 2.96. What did you guys get? Except for if you got 2.96, you should want to be yelling at me. Why can't my p-value be 2.96? It's a probability. It can't be bigger than 1. Your calculator will never give you one that is bigger than 1. So if you get something like this one that is in fact bigger than 1, you're going to look at the end and you're going to say, hey, that's in scientific notation. Now, How come we got the same p-value even though we got different test statistics? Well, the picture would look like this. For you guys, you got negative 4.168 and shaded this way. For me, I got positive 4.168 but shaded this way because I did the greater than. Are you guys comfortable that both these pictures come to the same conclusion? Okay? So, from the big picture perspective, it is very possible that when you guys read a question, you don't agree on what this is because you have these in the, like you might have this in the other direction, right? Because now that we have one on one side of the inequality and one on the other side, that's very, very possible. Okay? I am going to look, do your values here match the hypotheses that you wrote down? So you guys, especially because I know that sometimes you guys like to compare your homework answers, which is great. It's a good strategy to do. It's possible that you guys end up with different values here but the same p-value, and it's because you wrote these in the other order. That doesn't make one of you right or wrong. It's just different. I promise you I am smart enough when I'm grading your stuff to make sense out of that. Does that make sense? But it is, but what does matter is that whatever sign you have here is the one that you're putting in as that alternative up here. Okay, because otherwise you're going to get like 0.999, and that would happen if you had that going in the wrong direction. That was a lot of information. Were we good? Okay. Lastly, let's make a quick conclusion. We're going to say at 5% confidence, we can say oil changes are faster when conducted on the weekend. Noticing that I'm trying to steal the verbiage from the question as often as I can and add than during the week. All right, lovely. We already did that example. I put it in the notes twice accidentally. All right, but you'll notice that what we had here are two independent samples. There's no oil change on the weekend that can be directly compared to oil changes on the week. So what do we do when what we have are two dependent samples? Okay, so first of all, two dependent samples come from two different types of data. Paired versus matched. Okay, for paired data, we get two values from the same person/event. Matched data, we get two values from connected but not the same. Okay. For example, you'll hear a lot of oh, I did a study and it was a twin study. Twin studies would be matched because one twin and the other twin are two different people, but there's definitely something that connects those two people, right? Or you'll look at studies done for married couples. Those would be matched but not paired. Okay, paired data is like a before and an after kind of situation where both values are coming from the same thing. Okay, so, and when we do this, when we have matched and or paired data, okay, the way we run our test is different. So, let's look at an example. So, this example is about how long it takes to run 3 miles. And they had two different sets of runners. One time they ran it just like they normally would run it. The second time they did some sort of cooling technique, whether it be drinking like a whole thing of ice water or wearing like a cold vest or something that brings down their core body temperature, and then had them go run. Okay, so the idea is if you're starting off with a lower core temperature, are you faster? Is everybody good? The idea of wearing a ice vest right before running sounds terrible to me. But if this is actually true, I would totally consider it. So let's see. All right. So, you guys, is this matched or paired? This is matched. Okay. Because the times are from the same runner. Everybody good? All right, now, because of that, are you guys comfortable with me saying that these two numbers can be directly compared to each other? Whereas this one and this one would not be fair to directly compare, but these two I can directly compare, and then these two I can directly compare, and then these two. Is everybody good? Okay? Because these both come from the same runner, I'm allowed to do that direct comparison. And that's true for both matched and paired data. Okay. So what we're going to do is that. We're going to do that direct comparison. And instead of saying, doing a test on this set of numbers against this set of numbers, it's actually more powerful to look at that direct comparison. So what we're going to do is we're going to do their standard time minus the cooling time. Okay? So, I'm basically going to subtract 22.3 minus 21.9. Everybody good? I think that's 0.4, 0.4. Is everybody good? Now, we have to come up with a difference for every single one of these. Is everybody good? Now, I don't know about you guys, but sometimes that makes me really nervous. I'm probably going to put them in my calculator anyway, just to make sure I don't screw it up, right? So I'm going to show you something on your calculator that might make it a little bit easier. So what I'd like you to do for now is put the standard times in your L1 and the cooling times in your L2. Everybody good? Okay. So essentially what would be really lovely is if I could take every value in L1 and subtract L2 from it, right? Okay. So in fact, your calculator can do an operations on entire lists like that really, really quickly. Okay. So right now, if you go over to L3, it probably says L31. Okay. And that's saying what number do you want in the first line of L3? We don't want to change just the first line of L3. We want to change the entire list. So the first thing you're going to do is go up, highlight L3 at the very, very top. Notice it says L3 equals. There's no of 1. Okay? Hit enter. And what we want to do is tell it do L1 minus L2. To pull up the L1, you hit second 1. You see the blue L1 above it? And then minus, and then second 2 to bring up L2. So it says L3 equals L1 minus L2. I've been there.
It's just my eyes are so bad.
I've been there. It's the worst. And you'll notice if you hit enter, mine auto-populates. If you hit enter, it's all there. Is everybody good? And then, if you're going to be finding all those differences on your own anyway, you might as well just type both lists in and then hit that subtraction. You're less likely to screw up typing something in. It's already there. Is everybody good? All right. And so what we have is our list of differences. Right? And I'm missing one, it feels like. So I'll just throw it at the bottom there. But yeah. Everybody good? Okay. And so as you're looking at those, when we make so when we're doing these paired data, we're still going to write our hypotheses. But our hypotheses are going to be about mu subscript d for differences. Everybody good? And we're going to run our test on only the differences. Because those differences are more powerful than the two individual groups separate from each other, is the basic premise of that, okay? Now, as we go to do our hypotheses, the first one is that the cooling results in faster time. So as I'm looking at that, that makes me think that the standard is bigger than cooling. Would you guys be comfortable with that meaning that the standard minus the cooling would be bigger than 0? Okay? So what that means is my alternative hypothesis is going to be that the differences are bigger than 0, leaving my null hypothesis to be less than or equal to 0. Are we good? All right. For this one, we have one list of numbers, right? This is a question where I might ask you, draw your sampling distribution. Remember, for the two-sample t-test, I won't ask you to do that because your degrees of freedom is really wonky. And we'll just use the p-value method if it's a two-sample t. But if it's not a two-sample t, which it won't be because we're only doing it on one list of numbers and my hypotheses are about one mean, okay? Is this going to be z or t? Do we know the standard deviation of the population of differences? I don't see any standard deviation. We don't know any of them, right? So this is going to be t. And to find your degrees of freedom, you're going to think through how many values do I have that I'm working from? And that answer is how many values are in this list, which is 7. So what does that make my degrees of freedom? 6. And where am I going to shade? Right or left? To the right. Remember, I make that distinction. I make the shading distinction based on whatever my alternative hypothesis is. And how much am I shading? I say 5% level of significance. How would I find my critical value? Inverse t. When I go to inverse t, the first thing my calculator asks me for is an area. What area do I give my calculator? Here's a hint. It's not 0.05. Remember, inverse t only thinks in left-hand area. Okay? So if my right-hand area is 5%, my left-hand area is 95%. Degrees of freedom is 6. Are we good? Now I go to pick my test. I know I'm going to do a t-test. And the way I'm going to ask myself is I'm going to say, how many means do I have in my hypotheses? 1. So I'm picking the one sample t-test because I'm only doing it on one list of numbers. Okay? So I'm going to pick option number 2, t-test. A reminder, when you have mu sub 0, it's asking what is the value in that null hypothesis where the equal to is. Okay, in this case it's 0. It's asking me, in this case, because what we have is the raw data, but the data we're doing that on is this set of numbers that we currently have in L3. So if you hit second 3, it'll fill in L3. I'm going to make sure, double check my alternative hypothesis is greater than, so I'm going to make sure I have greater than highlighted. All right. I'm finding my t statistic to be 1.987, which is right about here. How would you describe this green dot of 1.987? I would call that in the rejection region, which is going to make me reject H0. So, reminder, this is the traditional method. My other option is saying my p-value is 0.047. What can we say about 0.047? It's less than 5%. My alpha, my significance level. Hey, if my p-value is less than my significance level, what does that make me conclude? Reject H0. This is what we call the p-value method. I will be mixing and matching the p-value method and the traditional method. Both are coming to the same conclusion, okay? Just different sets of reasoning on how we get there, okay? Lastly, our conclusion, I might say at 5% significance. We can say cooling results in a faster time for a 3-mile run. How we feeling? Are we good? I got one more example, then we're done. Maybe I have them backwards in my head right now. It's paired. It's paired. All right, so this is an example of a sample of 15 students. We got pre and post assessments, yeah? Is this matched or paired?
Is it paired? It's matched.
I think it's matched, because still both of these scores are coming from the same student.
Wait, what is paired then?
Yeah, because I wrote 2 values from the same person. Is that not what we said?
Oh, matched.
Was the other one paired too?
Yes, they were both paired. Okay. All right. You guys, we can choose. Do we want to do post minus pre or pre minus post? It does not matter. just need you guys to make a choice. Which one you want to go first? Which one you want to go second?
Post minus pre.
Post minus pre. Everybody picks post minus pre. Really hate negative numbers, right? Are we good? All right, so let's go ahead and find those differences. I'm going to use my calculator to do it. I'm assuming you guys would like to too. Okay, if we do that this way, if we're going to do post minus pre, now when we do our L3, we're going to do L2 minus L1 instead of L1 minus L2. And again, it actually doesn't matter as long as we know which one we're doing. Okay, all right. So based on what you can see from those differences right now, did the students make improvement? And what are we looking for to say that? Like, based on what we see so far, can we say that overall students improved? And what about this list tells us that? Most of them are positive, yeah? Okay, so if post minus pre is greater than 0, that's equivalent to saying that the post is bigger than the pre. So the next thing we got to decide is, one, not every single one of them was positive, and we had some 0. We have at least a 0. We see a -1. Is it possible that this is just by chance, right? So so what we're going to do in this case is construct and interpret a confidence interval. So this time we're going to do T interval. Again, we have the raw data. That data is in L3. So my interval is 1.692 to 3.508. If I want to interpret that interval, we can say with 95% confidence, we can say the population mean change in scores, right? This is not the population mean score, it's how much the scores went up, is between 1.692 points and 3.508 points. Y'all, what would my interval be if I did post, or if I had done my differences pre-test minus post-test? What interval would I get? Negative 3.508 to negative 1.692. I'd get the exact same numbers, they would just be in the opposite direction, okay? And so if I were to say, hey, we looked at our list and we could say, hey, most of the numbers were positive, that makes me think that the kids are growing. If I were to ask for you, can we say with certainty based off of the intervals that students made progress, that students' scores went up, can we say yes?
Yes.
Why?
Because 0 is not in the
I have a problem in this case of saying 0 is not in the interval. Because if this had been my interval for post minus pre, I could say that students got worse, not better. Okay? So in this particular question, it's not asking, is there a difference? It's asking, is the difference a good difference?
Yes.
Okay? So instead of saying 0 is not in the interval, we're going to say the entire interval is positive. So sometimes it's going to be about is 0 in the interval, but 0 if 0 in the interval tells us there's not a difference. It doesn't tell us where that difference is, right? Positive and negative tell me the direction of any differences that we see. The entire interval is positive, so the post-test scores are greater than the pre-test scores on average. That's what that tells us. And likewise, this interval, because the pre-test minus the post-test scores are all negative, would come to the exact same conclusion that kids grew. Okay? Are we good? Great, I'm done. It's likely that I'm not